we're ready, Marissa.
Thank you, Abdul, for the introduction. Okay, so let's get started. I just wanted to remind folks of the references that I mentioned yesterday. So the resources, so there's the primer, the notes on the complex of curves, and then these two papers of Masur-Minsky on geometry of the complex of curves, which will actually be kind of touching on some of the stuff in there during this lecture. Okay, so I promised you that today we were going to talk about some more complexes, some more quasi-isometries, and some more ways to use the curve complex. And so let's jump into it. So I'm going to just start with a zoo of complexes. So if you've taken a look at Saul's notes, then you'll recognize these languages. So let's just start off by remembering the ones that we chatted about yesterday. So I'm adopting Riley's beautiful highlighting technique for mine slides. Yay. So last time we talked about the curve complex. We also mentioned this non-separating curve graph, right? Where it's not quite the non-separating curve graph because instead of disjointness, we were having edges for intersection exactly once. Okay, but there's lots more than these. So lots more. For example, we have something called the arc graph or the arc complex. And here it's going to be the same as the curve complex, except instead of having curves out of the vertices, we're going to have homotopy classes of essential arcs. And then we'll allow edges for disjointness. And then we could have a combination of these. So we could have something called the arc and curve graph. So now we'll have vertices both for our curves, our essential simple closed curves on our surface, and also edges for our arcs. I mean, vertices for our arcs. And so this complex is actually quasi-isometric to the curve complex. It's pretty handy. We have, let's see what else. We have the Pants complex. Denote P of S. We have the marking graph. And we have one that I just want to mention quick because it's something that I've worked with in the past. This is, I call it the K curve graph. And this is just has the same vertex set as the curve graph, but now we'll have edges for intersection number less than or equal to K instead of for disjointness. So this is really just mentioning it because it intersects my own work. But there's tons of other graphs that are really naturally associated to a surface. This is just scratching the surface of the ones out there. The ones I want to focus on today are the Pants complex and the marking graph. So let's start with the Pants graph. Okay. So again, I'm going to denote it with this kind of slightly scripty P. And this is going to be the graph whose vertex set are corresponding to Pants decompositions. And whose edges correspond to I'm just going to put this in quotes because we haven't said what this is, and it can kind of mean different things, to elementary moves between these Pants decompositions. Okay. So I should say what I mean by a Pants decomposition. So this is going to be kind of exactly what it sounds like. We're going to take our surface and we're going to divide it up into pairs of Pants. So those are the three-hole spheres that I mentioned yesterday. So let's put on some curves. We just want to use essential simple closed curves. You can see I can divide it up into just some nice pairs of pants. So here's one, here's one, here's one, here's another. Okay, so here's my pants decomposition. So what is this a little bit more formally? This pants decomposition, it's, oh, wrong color. So a pants decomposition is a maximal collection of disjoint. Again, I want simple, so I don't want my curves to intersect themselves. Simple closed curves. So on a closed surface of genus G, this has size 3G minus 3. So these are my, this is what I mean by pants decomposition. Okay, awesome. So I've told you now what my vertex set for this graph is, but now I have to explain what I mean by these elementary moves. So these elementary moves really come in two flavors. There's two types of elementary moves. Okay, so the first type corresponds to a move that happens in a one-hole torus. Right? So if we have a one-hole torus and we have some, actually let me use this, some pants decomposition, one of our elementary moves is going to be taking a pants curve that looks like this red one I just drew, and switching it to one that looks like this. So we still have a pants decomposition of our surface, right? This is now a new 3-holed sphere, but we just swapped out those curves. And then my second one is going to be one that corresponds to a move in a 4-hold sphere. So you may remember these as kind of the special surfaces that had the fairy graph as their curve complex yesterday. And so the move here is going to be to take a pants curve like this and swap it. So that is one that looks like this. What's that?
There is a comment which says, I don't see pants in the second one. It's like, are those, that's a snap. Oh, okay, yeah.
Oh, should I draw the?
Yeah.
So here we have this, and then you can kind of open it up. So there's a hole here, and then on the other side, you see the other. And so here's the 3-hold sphere. It's a little less pants-like, but you can kind of pull those out and down, and you'll see the pair of pants.
Yeah. Someone asked that question before you drew the red curve in the second one, so it wasn't clear which pants you were talking about, but now it's clear.
Yes, yeah. Okay, awesome. Yeah, so see, so in both of these sets, we're preserving our pants decomposition. We're just moving some of the curves around. So these are our two types of elementary moves. And so let me just illustrate now a small piece of the pants graph. So these really should all just look the same. So each of these is corresponding, once I put a pants decomposition on them, each of these is going to correspond to one of our vertices. So here's a pants decomposition here. Here's a pants decomposition here. Here's a pants decomposition. And then here. And so now we can see that this is giving us a path here. These two are connected because we did this elementary move, swapping this curve with this one. These two are connected because, again, here we did a swap from this one to this one. And then finally, these ones are connected because of the swap from this kind of central separating curve to this non-separating curve over here. Okay, so one of the things I added to the exercises today was, because when I was writing this, I wanted to draw a like I was writing these notes this morning. Maybe I should have admit how last minute that is. I wanted to draw like an example of a cycle, but I didn't think of one on the top of my head. So I think exercise would be to give a cycle or a loop in the Pans graph. So I added this to the list. I'll just put that there. Okay. So this is great. This is like a very, you can kind of get your hands on it. Even though it's a little bit more, I guess, complicated than the curve graph in the sense that it has these kind of different types of edges that you see corresponding to these different elementary moves. Okay, so why did I want to focus in on the Pants graph? Well, I think it gives us a really neat example of one of the things I want to talk about today. So there's this theorem of Jeff Brock. And he shows that the Pants graph, well, he shows that the Pants complex. So you can also put higher dimensional faces in this, like we did for the curve complex, but I just want to focus on the Pants graph. It turns out that the Pants complex is quasi-asymmetric to its one skeleton, just like the curve complex. So it's totally fine for us just to be talking about the Pants graph. So he showed that this is quasi-asymmetric to the Teichmuller space of our surface, equipped with the Val-Petersen. I'm never sure quite how to say that. The Val-Petersen metric. So there's a bunch of different metrics that we put on Teichmuller space that are interesting to study. But one of the reasons that this is nice is because it gives us this relationship. So just as a brief aside, this is not something that we need for the rest of the talk, but I think it's worth mentioning, is the Teichmuller space of a surface S is the space of equivalence classes marked hyperbolic structures on S. So it's pretty cool that this like very combinatorial object is somehow capturing like this really great geometric information about a space that's so naturally associated to the intrinsic geometry of our surface.
So
Okay.
Riley is asking if this Pans complex gets 0.
Actually, I don't know. Is Teichmuller space cat 0?
I mean, even if it,
by Peterson,
It's not, right? Yes. It's negatively curved, I know.
I don't think
with
it's
the
cat 0.
Y Peterson, it is cat 0, but the action is like it's not complete with the V Peterson metric. But I get
Okay. Yeah, so this is a question we'll need to defer later. But I just want to point, like, say, kind of in other words, like, what does this mean? The important thing, none of this is important. The important thing that I kind of want to get at is that this is giving us, so in other words, the Pants graph is a coarse model, right? Coarse model for Teichmuller space, equipped with this metric, the Y-Peterson metric. So this is kind of the highlight here. This is pretty nifty, right? All these, yesterday we talked about all these ways of kind of using these kind of coarse geometric tools to study things. And so this is nice that we have something that is like such a rich geometric and topological object that has this like wonderful coarse model that is so naturally associated to our surface. And so this is kind of my goal now. My goal is to give a coarse model for the mapping class group. So this is kind of the guiding light for the rest of the talk. Okay, so I learned how to make a straight line, I think. Yes, okay. So this is gonna move us into the next section of the talk. So I told you there was 2 graphs that I wanted to dive into deeper today. One of them was a Pants complex that we just touched on. And the next thing is the marking graph. So the reason that I wanted to talk about the Pants graph first is because it's a little bit more straightforward. But it's in some respects very similar to the marking graph. So up next, let's talk about the marking graph.
Someone is asking if the quasi-symmetry is mapping class group equivariant.
Yes.
Okay.
Yes. Yes. So it's very nice. It's like as natural as you would want it to be. Okay, so again, I'm going to denote this just by this script M. And so this is the graph that has as its vertices. What happened? I turned it into a circle. As its vertices, markings, which we haven't said what those are yet. So never fear. And as edges, we're again going to have some type of elementary move. So these are not going to be the same as the ones we talked about for the Pants complex, but they're going to be reminiscent, I would say. Okay, and so really, secretly, this should say complete clean markings. So this is the language used by Masur-Minsky, who defined this. So again, this is where we're really getting into some of the work that Masur-Minsky did for the geometry of the mapping class group, or the curve complex rather. Okay.
Did we define a marking?
We have not defined a marking.
Okay.
Yes.
Cool.
So we don't know what a marking is yet. So let's do that. That's a perfect segue. So what are our markings? Okay. So a marking comes in kind of 2 pieces. So a marking U has 2 pieces. It has a base, and it has a collection of transversals. Okay. So this base is going to be something super familiar to us right now, which is it's going to be a Pants decomposition of our surface. Okay. And the transversals, so we have a transversal for each Pants curve. And this is going to be a little hand wavy. It's going to be so essential, simple, closed curve, which intersects. So it's kind of a signed Pants curve minimally. So really just once or twice. And doesn't intersect any of the other Pants curves. This was a weird way to write this. Any other Pants curves. And there's a more precise definition, but I don't think it's very enlightening. So I'm just gonna give this as the way we're gonna talk about them. Okay, so I think it's helpful at this point to just draw a picture. Right. So let's draw a Pants curve. Pants decomposition. So I'm just going to draw in red. We have our Pants decomposition. So this is my base here. And then I'll just draw in blue my set of transversals. So I'll just, like I said, for each Pants curve, I want a curve that's intersecting it minimally and that doesn't intersect any of the other Pants curves. What you would really like would be that you could actually have your transversals also be disjoint, but you can't do that, unfortunately, but you do want to kind of have it intersect minimally. So here's our final transversal for this middle separating curve. So it's disjoint from the other Pants curves, but it does unfortunately intersect the other transversals. And one thing to note is that a marking has finite stabilizer. In the mapping class. So this is really like pinning things down, right? We have our Pants decomposition, and then what else could we do? We could do some twisting, and those transversals, they are really picking up on that twisting. So this is great. Okay, so this is what I mean when I say marking. And again, this is a little bit not quite as precise as it could be, but I think this will get us where we need to be. Okay, so this is my marking. So let's revisit these like elementary moves.
So you said it's finite stabilizer. Is that like sort of sharp? Like, what do I mean? Is there a smaller number of curves that gives you finite stabilizers, or it's the smallest you can get?
That's a good question that I don't know the answer to. If anyone knows that off the top of their head, feel free to pipe up. Okay. Oh, can you repeat the question for Jesus, Abdul?
So I was asking if this is sharp, like if you have, is it possible?
Is it possible to have a smaller collection of curves that also has finite stabilizer?
That's right. Yes. Yeah, because you mentioned.
Do you know the answer to that?
You can unmute yourself, Jesus. If you want.
Yeah, feel free. Oh, yeah, exactly. I think Ian is exactly right. That you could just take a collection of filling curves, and you only need 2 curves to fill a surface. Great. Okay, awesome. Okay, so let's talk a little bit about these elementary moves. And just like the elementary moves for the Pants complex, these are going to come in 2 flavors. We're going to have twist moves. And we're going to have flip moves. So these twist moves, this is going to be taking a transversal I can say this in less words so I have more room. Take a transversal curve and twist it around its corresponding Pants curve. Okay, and then here we're going to swap a Pants curve with its transversal. Okay. So these are my 2 types of moves, just to draw a quick picture. So let's do the twist. So we can redraw the same Pants decomposition I did last time. So I had this, this, and this. And then I had my transversals in blue. So here's one of my transversals, here's the other. And then I'm going to just twist this. I'll do the twist move on this transversal. I'll twist this around its Pants curve. So it went from looking the same as the curve on like the right side of the surface to now being this twisted curve. So this is a twist move. And then the flip move, I'll draw a picture. And this is going to illustrate a bit of a more, I guess, a complexity here that we're not going to get into too much. So let me put my curves back. And so here, it's really just a difference in labelings, right? So we're going to switch this now to be my transversal and this now to be my pants curve. And so this is where I really need to put an asterisk on what I said earlier. Let me not be in gray. So here's an asterisk on this flip move, is that this flip move is a bit more complicated because actually you may have to do some surgery to preserve the correct disjointness and intersection relations that you're supposed to have. So this is not the final picture for the flip move, right? This is not the final picture. There needs to be some surgery that's happening there. But I'm not going to get into that because it just gets much more complicated. We'd have to do some, I saw someone say what surgery. So here, what I mean by this is curve surgery. So you might need to cut apart a curve and concatenate it with some other curves to like get rid of some of these extra intersections. Okay. But this is fine. We don't need to know too deeply what these are to understand kind of the big picture. Okay, so what are some handy things to know about the marking graph? So, well, one way that it really differs from the curve complex, right, is that this is a locally finite graph. Locally finite. We also have that map S acts on it with finite stabilizers. Luckily, it's also connected, just like, I guess, all of the graphs that we've looked at so far. And finally, we have that the mapping class group acts on marking graph, I guess, co-finitely, so it's finite quotient. Okay, and so these things all together actually give us something really nice. And this is exactly what we wanted. So this is a theorem of, as I'm sure everyone could guess, a Masur-Minsky. And it is that if we equip mapping class group with the word metric, you could take like the finite generating set we gave yesterday, the Humphreys generators. This is going to be quasi-isometric to the marking graph. So again, we have this, right? Wonderful kind of takeaway. So this is a really awesome fact, right? That again, we get that, oh, weird. That the marking graph this time now, this is giving us a coarse model. For the mapping class group. I guess again, we should just say, okay, so this is awesome. You get this kind of coarse picture. But it turns out we can actually get even more information, okay? So let's see now how we can leverage this. And so we're gonna take a little bit of a different flavor for the next little bit. And we're going to talk a bit about a tool called subsurface projection. So this is kind of, oh, how did I make it straight before? Perfect. This is a little bit of a different flavor from what we just talked about. Okay, so we've introduced these two neat complexes, right? The pants graph and the mocking graph. But like, isn't this a little early to abandon all hope for the curve complex, right? So we already highlighted a few issues, right? We highlighted that the curve complex is locally infinite. We also have that it's not actually, we don't have this coarse model aspect, right? It's not QI to the mapping class group. So the question that we can kind of pose for the next bit of this chat is, what geometric information about the mapping class group can we derive from the curve complex? We need some way to kind of refine the information that we're gleaning from our surface, right? Okay. And so let's talk about subsurfaces. So this is our kind of guiding question. Okay, so let's take essential subsurface Y. And for now, I don't want this to be an annulus. So this is a non-annular subsurface. And what I want to do is I want to define a way of taking information from the curve complex and projecting it down to the curve complex of this subsurface. Okay, so I want some sort of projection map. So I'm going to denote it pi sub y. And I want to define a way to map information or curves, right, from my full curve complex to now considering the curve complex of this subsurface. And so let's see how I can go about doing that. So this is what I want, right? I haven't defined what this is yet. So how I'm going to do this, I'm going to take a essential simple closed curve on S. And we'll denote its projection to Y, just like this kind of projection map notation. So pi sub y of gamma. So how am I going to define this? So if we have that gamma actually intersects my subsurface, then we have two options, right? Either gamma is actually contained in my subsurface Y. So it's contained in Y, in which case our job is pretty easy, right? So that means that gamma intersect Y is just equal to Y. And so we can just define this projection to be our entire curve gamma. Okay. But maybe it's not, right? Maybe it's not contained fully in Y. Then what does this intersection look like? So this intersection of gamma with Y, this is going to be some disjoint union of essential arcs in Y. Okay. And so what do we do here? Well, I think at this point, it's just easiest to draw a picture. So let's see if I can draw the picture. So here is my, that like, and that's supposed to look like a puncture. I don't know why I drew it so weird. And then I'm going to consider some curve. So this is my curve gamma. Here's gamma. And so let me just label this. So this is my subsurface Y. This is my curve gamma. And then let me just pick this up. Okay. So now let's see what happens when we do this projection. So what I want to do for this projection to define it is I'm going to take like a regular neighborhood of this collection of arcs in my subsurface Y. So what do I mean by that? So here's one boundary of my neighborhood. And here's the other boundary of my neighborhood. And so you can see kind of, let's see, in here, we have this kind of neighborhood that goes around. And so my definition of this projection, it's going to be the boundary of that neighborhood. So it's really that blue stuff here. Those curves, that's my projection of gamma to Y. So in general, right, in general, what am I going to do? Oop, let me not be in blue anymore. Is again, we're just going to do some surgery. We can, so there's kind of two ways to look at it. You can think of it as taking like surgeries of these arcs with the boundary components, or you can think of it as taking a regular neighborhood of those arcs and then taking the boundary of that regular neighborhood. Surgery these arcs together with this boundary. And this gives us a bunch of simple closed curves in Y. One note, like one caveat here, is these aren't necessarily disjoint. Okay, but they do have, so this collection, I guess this, if you think of this as a set in the curved graph of Y, it has diameter at most 2. So it's not necessarily disjoint, but it gives you this bounded diameter set. So really this projection map that I'm defining, this is not exactly a map, it's like a coarse map. We're sending a curve to a bounded diameter set in Y, and you could make like an arbitrary choice of curve in Y to make it an actual on the nose map, but like this, all the stuff we're doing is kind of up to some fuzzing, right? It's all up to quasi-isometry. So we don't mind that it's just a coarse map. Okay. So this is all great, but we remember that I had this kind of condition. I said that we're going to look at the non-annular subsurfaces. And so now we have to see what happens when we look at annulus. Okay, so next step, Y subset S is an annulus. And again, gamma is just some essential simple closed curve. Okay, so let's draw a picture. Okay, So we have kind of, there's lots of annulus, and we already kind of know that annulus are important, right? Yesterday we talked about Dane twist. Annulus see this twisting about simple closed curve. So for example, we could consider this annulus here. This could be a y. Here we see some twisting, or we could think about this annulus here. The problem is, let's zoom in on this y, is to measure this twisting, there's kind of easy ways to fudge things. Oh, actually, let me draw this after. So for example, we have our curve coming through here, but what if I did something silly to it? What if I took it and I just pulled it around? Okay, so now if I draw y prime again, right here, here's my y prime. It looks like we see twisting in y, but you can kind of see globally, we don't, right? This is not real twisting that we've introduced. And so what we're gonna do is what we almost always do in these situations, is we go to the universal cover. Okay. And so what we really get upstairs, I'm not going to go into the details of this, but you can build a, is actually, I have it as one of the exercises that you should make precise this annular subsurface projection, because once you kind of write down what happens, I think it's easy to see the picture, but it would take a little bit too long, a little bit longer than we have. So you get this compactified annular cover, which I'll call y tilde of y. And so then we can define this subsurface projection from C of S to C of y, where really this is, we're thinking of this universal, this cover. And then this, right, this is an annulus. So this was kind of an exercise I gave yesterday to think about like what I would actually mean by a curve complex for the annulus. Well, this isn't really a curve complex. This is an arc complex. So this is the complex with vertices, arcs. Here we actually want the arcs to have fixed endpoints. So we don't want to have, a lot of times when we think of arcs on surfaces, we think of homotopy up to like boundary slides where we kind of slide our endpoints. Here we want to actually have fixed endpoints. Right, and then again, edges are just normal, edges are disjointness. Okay, so it turns out that this is actually, this complex is Qi to the integers. And so there's really, this measures twisting about that, the core curve of your annulus. And so that's kind of the takeaway from this, is this gives you a way to actually see the twisting in a well-defined way that's happening about these annular curves. Okay, so maybe I'll just write that here. Measures twisting. Okay. Awesome. So why did I spend all this time talking about subsurface projection? Well, because it comes back around to using the curve complex as a way to interrogate the geometry of the mapping class group. So we've already seen a way, right? Let's just remember. We've seen a way to get at the geometry of the curve complex, right? So we had this result of Masur-Minsky that the marking graph is Qi to the mapping class group, right? So this is giving us a way to, let me just write down. Gives a way of, how do you spell interrogate? Interrogating, spelling on that. The geometry. So really, whenever I'm saying geometry here, it's really the coarse geometry of mapping class group. Well, it turns out that this subsurface projection gives us a way to get like kind of really refined information about this. Okay, so this is the last, here. Let's do some pretty highlighting. Okay, so this is the last thing that I want to mention today. And this is something that just comes up everywhere. It's a super helpful tool. So distance formula. Okay, so this is another result thanks to Masur-Minsky. So it's a little bit, I think this is the most technical statement I've made throughout the things, but the takeaway will is clear. But I wanna actually write down carefully what it says. Okay, so theorem. Okay, so we start off with a bunch of quantifiers. There exists a k naught greater than 0. This depends on our surface. This depends on the surface topology. This k naught. So that if there's a k greater than k naught, then there exists an A at least 1, B at least 0, with the following properties. Okay. So now we're going to take two vertices in our marking graph. So take two markings of our surface, U and U prime. Then we have this relationship between them. Their distance in the marking graph is coarsely equivalent. So these are this is my A is my multiplicative constant and B is my additive constant. So this is equivalent up to multiplicative and additive constants. So consistent with our theme of quasi-isometries. This is coarsely equivalent to the sum over of y over s of the distance, right? So these are the distance between U and U prime sub k. So what is this? This takes a little bit of unpacking. Also, my s just got taken away. Okay, so let's do a little bit of unpacking because there's a lot of notation here. So these are our essential subsurfaces. We are allowing annular subsurfaces. That's why we took time to define the annular projections. This is this like bracket, double bracket notation. This is a cutoff function. So here, if we put like some value x and k, actually, let me move this over so I have more room. So if we have x, k, then this is going to be equal to x if x is at least k and 0 otherwise. So this is so that this is a finite sum. And then what do I mean by this? this distance in y, so the distance in the subsurface. So this is why I defined the subsurface projection. So the distance in y between two markings, u and u prime, this is equal to the diameter of the projection of each of them. So this is the diameter of the union of their projections. And I guess one thing I didn't actually think of until just now, that is we're saying is, so I only talked about the projection of a single curve. So this is the projection of a multi-curve, right? And so here, this is just the, so if I had like a, I'm just writing this down on the fly. So if this is bad notation, sorry about this, but I forgot that this, I hadn't actually defined this. So this is just the projection of this multi-curve is just the union of the projections of each of the curves in it. Okay, so this is just it's kind of like what we talked about before. We're just doing it for each curve in our marking. Okay. So let me just scroll back up so we can let this, can I make this? Okay, yeah. So we can just let this sit for a moment. So this theorem is telling us that we can measure distance in the marking graph by summing over projections to subsurfaces. So we are able actually to get like this kind of very fine information, right? We can actually compute distances, coarsely, yes, but by projecting to subsurfaces. And so this is important because, right, this distance here, yes, I wrote this down for the marking graph, but this is telling us about coarse distance, right, in the mapping class group, because these are quasi-isometric. So we can actually, like, even though like the curve complex is not a coarse model for the mapping class group, it allows us to get this like really fine geometric information about it. So that's super cool. So let me just write down that punchline, because this is important.
Maybe we're maybe like you forgot to, so on the right side you wrote d sub y. Should that be like d sub c of y?
Yeah, so this is, so sure. Here, right, this is where I define my notation here. So that's just like a choice of notation. Yeah, you could totally write this if you want. It's just that gets super bulky. So usually people just say that's like the distance in the subsurface. Of course, since we're using the subsurface projection to measure that distance, really we're looking at the diameter of subsets of the curve complex of the subsurface. But so it's just a notational choice, just because that's messy to write. But yeah, totally. Macron, did you just, is there more questions?
There's a discussion on what you mean by essential.
What do I mean by essential? I mean, I don't want them to be boundary peripheral. So I don't want them to be homotopic into a boundary. And I don't want them to bound a once punctured disk. I don't want them to be homotopic into, so exactly. I just want them to be non-trivial, I guess, in the fundamental loop.
Okay, thank you.
Yeah. Maybe I should have reminded us all of that. Okay. This is important. So if there's other questions about notation or about something like this, I think now is a good time to ask that. I think I explained all the things. Okay. Cool. So now I just want to actually write it down, because for me this is a big deal and it just comes up. So like it comes up a lot. There's ways to characterize like actions of different types of elements of the mapping class group based on these types of distances. So again, I just want to write down distance in mapping class group. So this is just so that we can write it down without all the quantifiers. It can be approximated by summing over the subsurface projections. Okay. Awesome. So that's it. That's my punchline. This is where I wanted to leave off. And so you just highlighting that like these kind of very coarse combinatorial things can give us all of this information. So just before I end, just to give us a quick look at what's next, it's going to be very different. So we're going to take a complete like different tack. All the things that we've kind of like yesterday and today's lectures were kind of very close in flavor to each other. But tomorrow we're going to venture into new territory, and we're going to talk about big surfaces. These are infinite type surfaces and their corresponding big mapping class groups. So if you liked what we've talked about so far, you should come back because there's so many kind of analogies that we can draw. And if you didn't like what we've talked about so far, you should come back because it's going to have a lot of new flavors and a lot of new ways to approach. And I'm also hoping to talk about some open questions because there's a lot. This is kind of a new, I wouldn't say it's a new area, but it's an area of renewed interest recently. And so there's lots and lots of new directions and things to think about. Okay, awesome. Thanks so much, everyone.